My name is Stefan van der Walt. I'm a postdoc at UC Berkeley. I come from South Africa, where I'm an applied mathematician, or pretend to be at least. And today I'd like to talk to you about Scikits image, the image processing toolbox for Python. Scikits image is slightly different than many of the other projects you've seen so far. So projects like NumPy, Pandas, they're fairly widely applicable to all sorts of different domains. Scikits image is the only project here that's fairly focused on the specific domain of, in this case, image processing. The domain of application for image processing is vast. Image processing is used in science. You see it in microscopy, astronomy, biology. It pops up in computer vision, in engineering, and that's but to name a few. In industry, we see image processing happen in interesting places as well. Robots controlled in industry to perform automated inspection or control of production, used to process satellite data. At the Strata conference, there was a talk on augmenting sports television. So for example, when baseball players pitch, they want to know where did the ball land, what was the angle of throw, the speed, etc. And a lot of that is done with cameras following objects around, and a lot of image processing happening behind the scenes there. And then there are some toy applications, like when you scan these little micro arrays, the little black and white patterns that you see on conference posters, advertisements, etc. Some image processing happening there as well. For me personally, what makes this project so appealing is that we're really pushing the limits of what the current Python tools can provide us. We rely on base packages such as NumPy, but we actually require more than what those tools can currently provide. So we love programming in Python. We love what the current tools can do, but we need more than what they can currently provide. So we get quite excited by all the new developments that are happening in that domain as well. So like I said, we've got fairly high requirements of these tools. For example, speed is an essential requirement for us. People might want to do real-time processing of image streams or work on extremely large images. But without compromising on the aspect of speed, we also want it to make it easy for people to process images, to easily express the operation they want to perform in a high-level language, but still have it execute extremely rapidly. So for example, when Travis proposed yesterday a solution where you can inject functions into NumPy using something like LLVM, that kind of thing gets us very excited because we'll be able to program in Python, but still get the high performance benefit down the bottom. We often need to leverage different pieces of hardware available, like multiple CPUs, GPUs. We've got backends to utilize OpenCL, etc. Making use of all those platforms or all those hardware capabilities also pose some extra challenges. And then all of these things need to be exposed to the user in a way that doesn't make it difficult to use. We've learned a lot along the way in developing Scikits image. We've learned how to build robust pipelines, make it easy for users to string together a whole bunch of image processing functions and just have that work without doing any magic. In those pipelines, we need to very efficiently transform data, so interesting things happening there, and then deal with all the different ways that people represent their data. There are some subtleties when you represent images, like where is the center of a pixel? A pixel is a little block. You can think of it as a little block of color, or you can think of it as a data point. So is the origin of that data point in the corner, in the center? What kind of data types do you use to represent your images? We'll talk a little bit about that later on as well. And then finally, it's been an interesting experiment in building a small community. We're fairly small. We're like 4 or 5 active developers, and but we're not part of the big Scikits SciPy project at the moment. We're doing our own thing. We've got our own website and so on. So it's been interesting to see how that all came together. So if you look on the screen here, I've got a layout of roughly how all these components fit together. So most of our package is actually built on top of Python. So we leverage Python to get speed, and NumPy built on C primarily, also using some Python for the random number generation, for example. So like most of you know, on top of NumPy, we've got the higher level utilities such as SciPy, Matplotlib that we use extensively, and yeah, on top of that, Scikits image. ND image comes from, I think it might be from NumArray. It was developed in the astronomy community, at least by Peter Verveer. It was integrated into SciPy. But ND image is written in pure C. It's a little bit hard to get people to develop on ND image because it's hard to wrap your mind around it. So with Scikits image, we try and make a much easier entry point into image processing and aim to vastly extend the capabilities of ND image. So just to give you an idea of what is available in SciPy, so in ND image itself, let me well, let's go to if you just go to the SciPy docs. Right, so you see in the ND image package, we've got ND image filters, so just common filtering operations, filters relying on the Fourier transform. There's some interpolation that we need when we do geometric transformations on an image. So when you warp, when you skew an image, when you apply spline filters, for example, and then some methods for doing measurements on images. Like if you've got a whole bunch of image areas, how do you measure the size of those areas, how many there are, etc. And we'll see an example of that just now. Some morphological operations, they operate on the structures inside an image, and yeah, that's about it. So what I'd like to do is to run through a typical example of how would an industry problem look, and how would we solve such a problem. All right, so I'm going to import ND image as NDI. Right, so there's the problem definition that we have. Where's my image? There we go. So this is the image we'll be working with. It's a microscope image of some heated up glass. So there's a description. They say that this specific glass sample, the glass is the light gray background that you see there. There's some bubbles, black bubbles in there, and unmolten sand grays. Those are the slightly darker gray that you see in between. And when you've got a slide like that, what you typically want to do is count how many different types of each phase there is. So what area of this image essentially is covered by the light gray glass background, what fraction is covered by the black bubbles and by the sand, the dark gray, how many bubbles of each kind, what's the average size of the bubble, how many bubbles are there, that sort of thing. So how would we approach such a problem? Well, the first thing we need to do is we need to get the image from the disk into the computer. So can you all read what it says here, or should I make it a bit larger? It's okay? Yeah. Right, so we start, in this case, I'm just going to use ND image and Matplotlib to show you what those tools can do, and then I'll show later on how Scikits image builds on top of that. So we load Matplotlib. We're just going to use that to read the image. We import NumPy as well, and we use Matplotlib's imread function to read in the image. And then we display the image. We specifically set the color map to gray because by default there's, I think, which is the default color map, John? It's jet, right, typically. So you see like a whole bunch of colors usually if you try and display a gray image. So we set it to gray by default, and importantly set the interpolation to nearest, because otherwise if you zoom in on the image, it will smooth it out as it interpolates those points for you. So we just set it to nearest so we see the exact pixels that we loaded in. The first problem we have is that the microscope inserts a banner here. So we just want to get rid of that banner. That's fairly easy to do with NumPy. The image we loaded is simply a NumPy array, so we can apply all the standard NumPy operations to it. In this case, I just choose to take the first 880 rows, throw the rest away. So that's the part of the image without the banner. So there we go. Okay, so just discarded that bottom bit. Now, you'll notice that you can't really see it on this on the screen too well, but there are a whole bunch of speckles inside these black blobs that we don't want. So how do we get rid of those? Well, in this case, I ran a median filter on it. A median filter is basically just a windowed operation. So you slide a window across the image, and inside of each window you say, let's pick the middle value. So you sort all the values, you just pick the middle value. And that tends to get rid of speckle noise, very high and very low values. So, so that's what we do next. Right, and there you can see the phases seem to be much cleaner. We don't have as many speckles lying around. Now, the next step we need to do is to separate out those three phases. So we've got the light gray, the glass background, we've got the black blobs, and then sort of the dark gray sand grain. So how could we separate those out? What could we do? Any suggestions? Yeah. Oh, I forgot that you guys can see the solution. Right. So what we want to do is we want to basically set up three different masks. We want to threshold this image in two different places, basically take all the darker pixels, all the lighter pixels, and then the gray pixel in between. But we don't know where to take those thresholds. So the way we investigate that is to plot a histogram of all the values inside the image. And when we do that, you can clearly see that there are like three different modes here. So this would be the zero intensity pixels, so those are the black blobs. These are the darker gray sand grains, and the white here, or the light gray, is the glassy background. So where would be a good place to threshold? I think I picked 50, so took those values out, then all the values between 50 and 120, and from 120 upward. Right, so that's exactly what I do here. I say, create three different masks for me. This operation, it's a truth test. It says, is the median filtered image less than or equal to 50? So that will return a Boolean typed ND array for me. True or false values will be a mask for the bubbles, the sand, and the glass. And then I just have a little bit of code there that plots all three of those. Right, so there we go. We see the original image, we see the bubbles isolated, we see the sand, and we see the glass. What would be convenient is if we could take all these layers and combine them into a single visualization. So how would we do that? Well, typically we represent images as an m by n array. And that array then just contains intensities. But you could also make an m by n by 3 array, and those three layers would then be red, green, and blue. So we construct a new empty image of the same shape as the original, except we add that extra dimension of RGB. And then we proceed to fill those layers with different values according to the masks. So wherever there are bubbles, we write the value red, no green, no blue. For sand, we add red and green, but no blue. And for glass, no red, no green, and full blue. There we go. All right, so that gives you a very nice, convenient single representation of your different phases, much easier to recognize than on the original image, and it also shows you what you labeled. Now, if you notice here on the edges, you still have some yellow coming out on the red. So there's still some mixing up on the phases here on the edges, and we'd like to get rid of those. So what we're going to do is apply a morphological operation. Morphological operations change the structures inside an image. So we're going to try and get rid of these little speckles. We do that again by moving a window over the image and saying if there are structures that aren't entirely contained in this window, throw them out. What that typically does is it tends to grow structures inside the image. So we actually change the size of these bubbles. So then we basically do the inverse. We say move that structure over the image again, but everything, everything that is not contained, select that. So then we shrink the structures again and hopefully get rid of these extremities without changing the size of the bubbles too much. So we apply what they call a binary opening and a binary closing. And there's our final phases that we're going to work with. All right, so what's the next step? Now we want to figure out, we know we've got bubbles, we've got sand, and we've got glass, but how do we count how many bubbles there are? How do we count how many sand grains there are? What's the average area of those things, etc.? So the first thing we do is we label our components. So we go through this image and we say, identify all the isolated blocks or connected blocks of pixels and give them different values. So we'll start and we'll say, here we've got a blob of pixels. We'll label that 1. The background is typically labeled 0, so this will be 1. Scan, 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 scan. There's another one that's 2, 3, 4, 5, 6, 7, 8, 9. So we'll just consecutively label the different connected components in the image. Right, so that's what this call here does, ndimage.label. It steps through the image, labels all of them, and then we have this single line of list comprehension to calculate the statistics we want. So it says, for each label I in the range from 1 to the maximum label, find all pixels with those labels, so where the labels are equal to I, and just count how many of those there are. So that gives us our number of object areas. All right, so there we go. These are the labeled images. They're plotted with the very useful spectral color map, which changes fairly rapidly over the integers, so you can see all the different colored bubbles coming out here. The glass is mainly a single blob. It's the background, and then some others coming out, but mainly the big background one. Lots of sand grains, and they are the statistics. So 150 regions found in the sand, 70 in the bubbles. That makes sense. So we've got more sand than bubbles, and many fewer in the glass phase. And as we expect, the glass phase has got an average, a fairly high average size because it covers almost the whole image. And the sand grains are typically very small, but there are plenty of them. Right, so that's a typical image processing pipeline that you might form. So I hope that provided some insight. Now, Scikits image builds on top of the SciPy and ND image tools. I'll show you the homepage for the project. Let's go there. So there we go. This is a pretty standard template. You'll see the IPython webpage looks very similar. We kind of borrowed from them. And so you can download the project here. We've got our user guide, a gallery of examples, where to get the source code. And just a trivial example on the front page so you can get started quickly. I encourage you to go look at the gallery. It's probably one of the most fun places to browse around and just see the kinds of things that people have done. This isn't an exhaustive list of what's available in Scikits image, but it does give you a quick preview. So for example, we've got a marching squares algorithm. So if you've got a height map of some sort and you want to follow contours along that map, you can use the contour finding. We've got numerous edge detectors, and here's an example of some histogram equalization. So if you've got an image such as this one with very low input contrast, you can choose different ways of scaling it. You can either try and linearize the cumulative histogram, or you can just sort of stretch the contrast a little bit to provide an image like that. We've got some, this is a cute example where we took a natural image, just split that image up into little windows, and then did k-means on those images, those sub-images as features. And you see when you do that on the original image, you basically get something that looks like Fourier components. But when you do that on the edges in that image, or the difference of Gaussians, you get these Gabor-like feature, code book coming out. We've got the Huff transform for doing straight line detection in images. We've got radon transform reconstruction. So that's when you do a CT scan of the brain, you scan the brain from all the different directions, and it sums it in all the different directions. That gives you something called a sinogram. And based on the sinogram, well, this is what your scanner gives you. And if you want to invert that, you do some filtering, you do the inverse radon transform, and you can do a reconstruction of your image. Then some segmentation, feature detection, denoising. Yeah, so that gives you a rough idea of the kinds of things we do. So here's a typical example. From the Scikits image module, I imported data, filter, and I/O. So data is where we typically get our sample images from. So in this case, I used the coins sample image. Then I applied the Sobel filter to that image, and I display that image. There we go. So io.imshow typically makes use of matplotlib by default, but we've got a whole variety of different output modules that we can use, output plugins. So you can display using Qt or matplotlib or whatever's available in your system. We just basically want to make it easy for users to display images irrespective of what they've got installed. But you could just, it's a NumPy array, so you can just display it using normal matplotlib. That would work fine. In the same way as we have output plugins, we've also got several input plugins. So you could use the Python imaging library to perform image reads by specifying io.usePlugin pull imread. And then when you read the image, it is read with the Python imaging library and not with matplotlib. So some libraries allow us to do interesting things. In our Qt backend, we've got a fancy imshow. So if you decide to use plugin Qt for image display, and you specify the fancy parameter equals true, you'll see something interesting happening. We've got, we pop up a little display like that. So your image is displayed with histograms on the side. These histograms are updated if you adjust the colors in the image. You can see, look at the red histogram as I just the red component. You'll see that it goes higher up. This all happens in several processes. It splits up the process to more rapidly process the image. And if you notice here at the bottom, you can follow the position of the pixel, the value, the position at the cursor, the value, the RGB values at the cursor, hue, saturation, value. All right, so let's adjust the image somewhat. Let's go to gamma, and well, let's first adjust. I'll add some green to the image. Just slide that up a bit. Then this is a little bit like revision control. You can choose to commit your changes, or you can choose to revert them. So you make cumulative changes to your image, and you can move up and down that stack. So there, that's committed. Now we can go to the gamma adjustment and just push up that gamma value way up or way down. That looks kind of cool. Let's do that. And then here's a button called Save to Stack. So we've got, well, let me commit that and make this thing a little brighter. Yeah, okay. So I'm going to click Save to Stack. So we keep an image stack around. If you push images onto that stack, you can now go back to your notebook and grab the image off the stack and manipulate it further. So I'm going to close this viewer, and I'm going to go back here, and I'm going to say io.imshow io.pop. So io.pop goes onto the stack where I just push that image, grabs it out of there, and then we can display it. So often you want to read files coming from different domains. Like in astronomy, they use the FIT image file format. You might use DICOM images if you're working in the medical domain. And we've got different plugins for these. So in this case, I'm going to say use the plugin FITS, and then try and read this star image. And yeah, there we go. There's the image. Now, one of the biggest problems we've had with, oops, I want to do that. One of the, did I just kill my notebook? Oh dear. So people use images with different value ranges, and this becomes quite problematic. For example, typically you'd store your image as a floating point array, and all the values would be between 0 and 1. But other people store the images as unsigned integers ranging from 0 to 255, or bigger integers running from 0 to 65535. Some people store the images running from -128 to 127. So how do you deal with all these images in a way that's not too confusing to the user? So we basically support all of these, but we assign very specific expectations. We say, like, if your image is in floating point format, the values must be between 0 and 1. Otherwise, we don't know what you mean. So we've got several conversion functions. So you can call images float, images unsigned byte, images unsigned integer, or images int, and it will convert your image to that new representation, taking into account the ranges of the image. And these functions are typically called at the beginning of any filtering operation. So the filtering operation takes in any image, any data type, converts it to what it needs, and then spits out whatever is most convenient. But because all the functions take in any kind of image, you can string these together, and it should always just work out of the box. So I guess my kernel's still running. So yeah, so it's all fine. So here's the NGC image that I just loaded in, the star image. And if I print the minimum and maximum, you'll see that it ranges from 100 to 65535. So that was actually an integer image. But the fits plugin, the fits pyfits library in Python returns a floating point. So we wouldn't be able to handle an image like that because the values are outside the range 0, 1. So if you try and filter an image like that, you should see an error. And that's what happens. It tells you, well, your image should have been values between 0 and 1. But to handle that, we've got a function called rescale intensity. So if you know what the ranges of your intensity are, you can call this function. And in this case, I didn't provide any parameters to tell it what the ranges are. So it just picks 100, the minimum value in the image, sets that to 0, picks 65535, which was the maximum value, sets that to 1, and returns that for you. So if you try and filter the returned image, should be no problem. And yeah, that's what we see over there. It's no problem. You can also tell the rescale intensity function what you expect the range of your values to be. So we've now changed this image to have values between 0 and 1, but we can tell it, well, let's say the maximum was 0.25 instead of 1. So what would that do? That would discard all values above 0.25 and stretch 0.25 to be the maximum value. And when you do that, you see that this is a much brighter version of our original image. So here's an illustration of the conversion functions. I took that image and I first converted it to float using image as float and printed out its maximum value. You can see it runs from 0 to 1. Then I converted it to integer. You can see it runs to the maximum integer value, or if you convert it to an unsigned byte, it runs to 0 to 255. Now, often when you want to test your algorithms, you need access to some test data. So we provide several test images in the data subpackage. So if you import the data and you use data.camera, for example, you get this guy out. Data.coins is this image. And if you call data.coins question mark in IPython, it just loads the doc string for you. And you can see that we've got, says those are Greek coins from Pompeii. It tells you a little bit about the history of the image, what it's typically used for, and what the copyright situation is, where it was obtained from. So if you want to use it in your paper, we try and use images that are freely available, so you don't have to worry about that. So like I said, it's important to image processing users to be able to construct a pipeline without any hassle. And if you work with ND image, for example, you constantly have these problems where you convert an image, but the range is outside of what was expected. So if you, for example, take an image, you multiply it by 2, and you display it in matplotlib, you typically won't see any difference because there's just some automated scaling that takes place. So that's why we have these functions that make sure that if you multiply your image by 2, you actually see the twice the intensity. So let's look at this example of constructing a pipeline. I take the camera image that I just showed you. I don't know what format that is in. It doesn't matter. The canny filter knows how to handle that. So that's what's plotted over here, just a plain edge detection. But if I first want to apply total variation denoising on my image and then do the canny filter, I can just string them together like this. I don't have to worry about the ranges, the data types, nothing. That's all taken care of. I just string them together. That's my pipeline. And when I display the result, there it is. So you can see if I just applied the canny edge detector, detected a whole bunch of spurious edges. If I first denoise the image and then applied much cleaner edges. One of the algorithms we implement is called shortest paths. And I want to show you this video on how shortest paths are typically used in let me try and make this. I'll just sort of narrate as he goes along. He's doing a context-sensitive resizing here. So he's explaining that on a typical Wikipedia page, if you shrink the page in width, you'll see that the image remains constant in size, even though the text reflows to fit nicely. So this is less than ideal. Here's an example of a bear and a cub. If you try and shrink that photo, you typically end up with a difficult situation. You either have, you crop the image, so you cut out a piece, so the bear is here, but the cubs are over here, you can't see them. Or you scale the image, but then everything is kind of squished up, or you cheat a little bit and you retarget. So here they took the image, they're trying to change the aspect ratios, and so this is the retargeted image. This is what happens when you just squish the there's the image squished, and this is the image cropped. So you can see that over here you've got all the content you want, but without changing the aspect ratio or losing too much of the image content.
We also define a flexible multi-size representation for images that supports continuous resizing. An image can be shrunk in a non-uniform manner while preserving its features, but it can also be extended.
So you can see that all the features remain inside the image, even though we're rescaling it. Even if you stretch it out, so he wants to shrink the width of this image of the blocks. How is he going to do that? So what they show is that they do edge detection on the image first, and that helps him to decide which parts in this image can we carve away. They call this technique seam carving. So the idea is that your eye is much more sensitive to edges than to smooth areas. So if I took out a path in this image that ran here, avoiding all the edges, then my eye probably wouldn't notice what's going on. So I think it's first going to illustrate now what happens when we just take away columns in the image.
This column by defining an importance or energy function on the image. In this example, we use the gradient magnitude of the image. Next, we look for the column which contains the least energy and remove it.
Right, so it's now just removing columns depending on the columns that cross the fewest gradient, that crosses.
From one side of the image to the other that contain the least energy. This can be done using a simple dynamic programming algorithm as described in the paper in both vertical and horizontal directions. Here's another example of an image, its energy function.
So there's the edges again, and then they detect the path that runs along the fewest edges, and they keep removing those one by one. So blue to red is just the order of the seam removal, so you can see which ones are removed first and last. And here he inserts pixels to grow the image. This is a good example. They try different things using edges or saliency or whatever, but in the end, gradient magnitude seems to be fine for what they're trying to achieve. Sometimes features get removed from the images that you don't want removed. Like in this case, look at the baby's head, that wasn't too good. So you mark the areas that you don't want to remove, and they basically get increased penalty values, so they don't get selected for removal. This is a great example. Like, if you don't want that guy in your picture, you can actually select him and say, like, we'd prefer the cost path to go through there. So gone. There we go.
More examples can be found in the supplemental material. Thank you for your attention.
Right, so that's a technique called seam carving, and we actually have an implementation of this using the shortest path algorithm in Scikits image. Often we want to geometrically transform images as well, so you might want to take an image and downsample it. So in this case, I started off with the cameraman image, and I called ndimage.zoom with a zoom factor of 0.1, so scale down the image by 10. And when you do that, you get this as output. You can see this is much more blocky than the original. Sometimes we want to be a little bit fancier than that. So in Scikits image, we have the transform module that does all sorts of different transforms. We can specify this transformation matrix here. So it's a 3x3 transformation matrix. This matrix is applied to each coordinate in the image, and whatever comes out, that's where the coordinate is moved to. So those of you with a background in linear algebra will recognize the first 2x2 subblock of this matrix as a rotation matrix. We've got cosine, minus sine, sine, cosine. The s's in there are just for scaling x and y. We've got translation parameters here, tx and ty. That's for shifting the image around. And then some skew factors, S0 and S1. So if we just want to do zooming, like in the previous example, we simply set S equal to 0.1, and then we shrink the image down by 10 times. So let's do that. We call transform.homography with that matrix, and there's the output. Now you'll see that I cropped the output by just selecting the first 50 by 50. If I take that out, you'll see what's really going on in the background. We take the image, we size it down by 10, and that's what's stored down there. But you can do slightly more interesting things. You can rotate the image. So let's say we want to rotate it by 15 degrees, maybe translate it by 100 in each direction, and add a small skew factor. So, large skew factor. Oh, my scale is still 0.1. Let's not do that. So I'll set the scale to 1. There we go. So there you've got a linear warp of the image. Now, ndImage also provides a map function, because this is a linear transformation. All straight lines in this image remain straight lines over here. And sometimes you want to do nonlinear transformations. So there's the coordinate map function. And let me see if I can execute that demo. Right, so here's a photograph of a window frame, but you can see that there's severe distortion on the edges of this image. These lines are supposed to be straight, but they are very much curved, and we'd like to pull them out. So what I do is I provide the script with the straight lines. I mark 3 points there, 1, 2, 3. And let me do another line. So 1, 2, 3, and then there we go. So based on those, I gave it three coordinates and asked it, please optimize the warp so that those 3 points lie in a straight line, and this is what you get out. So I didn't do a very good job of marking, but these lines are much straighter than they were in the original input image. Recently, we've also added support for block views and filtering. So often you just want to slide a window across your image, do some operation on that window, and return the result. So if you look in the shape utility, you import view from window, view as windows. You can take your input image, view it as a bunch of windows, so that's the sliding window. It's just a view in the original image, so there's no copying of data taking place. You can do this on a fairly large image. Specify the shape that you want. Your input image is 512 by 512. You now break it up into blocks of 20 by 20. So your output is 493 by 493. It's almost the size of the original input image, but these windows have to fit inside the image. And each block is 20 by 20. And then you can do some operation on that block, like you can get the maximum of the entire block. And if you display that, there we go, you get something like that out. So you can clearly see the blocky structure of that filter coming out. If you're looking to detect features in your image, you can call the HOG, the histogram of gradients on it. That basically examines the image at each pixel position, and it looks at the gradient and it counts the number of gradients in each direction. And here's a visualization of that. Brighter pixels indicate more gradient found in a certain direction. So you can basically see the original structure of the image coming out. Lots of vertical here along the pipe, and horizontal, and more vertical along there, for example, on his shoulder, because the gradient runs horizontally there. Right, so I think that's about it. If you're interested in image processing, or you can use some of these utilities, feel free to get in touch with us. We like to welcome more people into our community, and the mailing list is populated by guys who know a lot about image processing, so feel free to come and ask questions or just discuss the tools we're using. Seems like we're done. Right, thanks very much.